I do this afternoon.
Thanks for helping me out with that ethics, by the way.
Oh, yeah.
We're
See,
going to go through
today.
Oh, I thought we were
You have to
doing-
call me everything.
Okay.
So like I was lost, I didn't know what I was doing.
Yeah. So there's another one due tonight.
Yeah, I was working on it last night. I'm gonna probably finish it up.
Yeah.
Okay,
It's
let
just the
me
one, right?
go get my pen.
7 thoughtful comments.
BS.
Yeah.
Very inspirational, heartfelt comments on everything. 7 of them, really? And then he told us we got credit for that day, right? He's like, I still haven't heard from you guys. We're like, because I already have credit.
It's only
Dude, I kind of assumed that we didn't have to do the forums, the like discussions,
Yeah.
if I got my full credits on the first day. Nope, that's not the case.
No.
That is not the case.
I don't know. I'm just trying to get over with it. So.
Yeah.
I think his class is gonna be fair though.
Yeah, he seems to be a fair teacher. So.
Like even when I'm like way out in left field, he kind of brings my explanation back, which is cool.
Okay, don't forget to do attendance.
We marked it.
Will you please? Yeah.
Yes.
Yes.
Really not
Yes.
fair at all.
I already got a social science, I'm double practicing.
Caden,
That's what the economics.
Lynette,
so, social science.
Jack.
Social science, social media, writing.
Kyle, do you want me to do your
Yes,
attendance?
please.
Yeah, you do mine as well.
Mine's gonna try and sign on to the internet for another 30 minutes.
Anyone else need me to do theirs? Okay. All right. Any questions before we jump into doing some neutron life cycle calculations?
Oh, yes.
Yes.
So during the resonance escape, do all neutrons go through that epithermal phase, or?
They all do. But what happens is the ones that get caught up here in the peaks, those are the ones that essentially get stuck. So if they
So if they do
are
get stuck.
under this curve, they can continue down to thermal. Those ones that get stuck, they never slow all the way down.
So
to
then they'll
thermal.
just stop like right here.
Yes.
Oh, okay.
Mhm. So if they escape the peaks,
Right.
they thermalize.
Okay.
Resonance escape probability.
Is that what it's called?
Mhm.
Oh,
That's that P term in our
the
six-factor
P is
formula.
probability.
Resonance escape probability. Yeah. Okay. So let's start. Who wants to draw our little neutron life cycle circle up here? Put our 6 factors up there so that we can do a calculation based on those factors. Is that what you're looking for? Mm-hmm. Yep. There's a
Yeah,
volunteer.
they're all written out. I think you should do it.
I'm looking around, I'm going.
I think you were at the board yesterday though, right?
Yes, maybe
So
somebody else should
let's
do.
have someone other than Kyle and Cattell. Okay.
I'll
Kate.
do it when my computer turns on. It's being weird. But I don't have it written out and I don't remember it, honestly,
Okay.
because it's fresh, you know.
Because it's fresh.
Come on, computer. Oh, it's updating.
Does someone who doesn't have an updating computer want to do it?
So the circle, do they have to go in that order? Because they're all like happening like simultaneously, right?
So there's going to be so many fissions occurring that they will be happening simultaneously. And even though they are going to progress in order, because you first have to fission and then you have to lose your fast neutrons and then they have to slow down, right? there is an order. So yes, it does need to go in order, but it's gonna be happening so fast that we couldn't identify each step, essentially. Was that you volunteering, Jen?
Glad I'm pulling it up. Never mind.
Joe, Jack, Sam, Haley,
This is right.
I do not
yeah,
volunteer.
that one. Yeah, or that one.
Yeah,
Ready?
I can draw it.
Okay.
Wait, do you want this one or the other one? There's two on here.
Which
one do you prefer?
I like the one that Joe has best.
Okay.
The other one.
This one.
When is that, INL, is that tomorrow?
Tomorrow. And the extra credit seminar is also tomorrow, just before that.
What haven't heard of that?
That's the, I sent you guys an email about the low dose radiation,
Oh, that's online?
the Zoom, yeah. We're gonna play it in this classroom at 10.
Did you send that recently?
I think at the end of last week is when I sent it. I can send it out again.
When is John's thing?
So it's on a Friday instead of capstone because we needed a 2-hour block with you guys.
I don't like the way they self-absorb absorption.
I Googled it and with the P, it's correct.
So I think there's a British and US spelling.
Will you send that email again?
Yeah, I don't think I received that.
Is the INL one extra credit too?
It's not. It's just in your best interest.
You know what I found interesting? They're posting jobs for every other program except for ours right now.
So a lot of times they do try and coordinate their postings with graduation because they had some that they posted like way back in January and February, but then students weren't ready to start, which seems silly because they didn't process the things until May because I know it's slow. So I think they've moved when they post to closer to graduation because we haven't gotten the email that they've opened the ESTech specific posting yet, and they usually
Yeah,
tell us.
there's not anymore.
Yeah.
I think this thing needs to be calibrated.
How many do they usually open up?
They usually have one posting and then they're looking to hire some number more than one. So out of that posting, I think last graduating class, they hired 3 people from it.
Do you know what email it was?
Like all of you have 2 emails now because ISU did the change thing. So I've been sending them to your old emails that I used last semester, which I thought would forward to your new ones. I'm sending it again right now though to everybody.
I just think my email changed.
I know that just before the semester started, I sent an email to Joe's new email alias that he didn't get.
Sometimes I send stuff to Haley though that she never receives it. I just send it like through.
Okay. I sent it again.
There you go.
Okay,
How come we couldn't pull one up?
because I wanted you
Oh.
guys to be doing this. Let's see. Okay, so what's the symbol for our fast fission factor? Epsilon. What's the symbol for fast non-leakage? Right, 'cause this is what leaks, so it continues on is our non-leakage.
It's not one, never mind.
This over here, if I was tall enough to write where Caden wrote, this would be 1 minus L sub F. This is the L sub F,
That's non-linkage.
non-leakage. It's the fast non-leakage factor, so what doesn't leak continues on to our resonance escape probability. What's the symbol for resonance? P. Over here, what's happening to these neutrons that
Is that-
don't slow down?
Is that like poisons?
Not yet. Poisons are gonna get over here.
Four in the structure.
Say that a little bit louder.
Using the poison to four in the structure.
No, that's gonna happen down over here. Joe?
Are they getting absorbed by U-238?
Yes.
Oh,
So these are our fast neutrons that haven't slowed down. So they're gonna be fast in the U-238. Let's actually choose one other color. So this is absorbed in the U-238, or these are trapped as epithermal neutrons in our resonance peaks. Okay? So whether they're absorbed by U-238 or trapped as epithermal neutrons, they don't slow down. Okay, once they slow down, we're going to have a certain amount leak. So what's our term for those that don't leak?
LCD.
L sub F.
L sub T. This is thermal now. And when I first learned this, we actually wrote it L sub TH. And sometimes I might do that by habit, just so you guys know. This is all you need to write. Is the L sub T. But if you see me occasionally write L sub TH, it's a habit, because that was the old way we wrote it. Okay, so right here, what leaks? What's our term for what leaks? Right? Same as this would have been 1 minus our L sub F. So here, we have our thermal neutrons that get absorbed. Some are going to end up absorbed not in the fuel. So what's our term here? What's this factor called? And what does it stand for? Thermal utilization. So the thermal neutrons that go anywhere but the fuel versus the ones that go into the fuel. Because we're going to be able to use them if they go in the fuel, right? So now they're in the fuel, and we're going to fission. So what's our term here? Eta. And what is that term called? Thermal reproduction. is we're gonna make new fissions. And we're going to do a calculation, and the standard I'm gonna use, so we know clearly what generation we're talking about. This is our first generation of neutrons that go into this cycle, and this is our second generation of neutrons when they come out of that cycle. Okay, so our first generation is going to go in, we're going to have all these things happen, and we're going to have our second generation come out. When we do a problem like this, what I'm going to do is I'm going to give you values for these factors. So let's say, and I picked values that are fairly similar to what you would normally see in a thermal reactor with U-235 fuel. There's not a lot of variation except in what we can control as operators, because most of these things are controlled by the design of the reactor, right? This is decided by the fuel we use. This is decided by the fuel we use. This is decided by how big our core is and whether or not we use reflectors. Same thing here. Size of the core and presence of reflectors. This is a property of the fuel. This is a property of the types of materials we use in our clad and our moderator. This can be affected by the moderator. This can be affected by putting in or taking out control rods. So this is really the only one that changes in operation. Most of the rest of these are going to be pretty constant based on the design of the reactor. You have a little bit of change that occurs as temperature goes up, because you'll mess with the energy a little bit that's coming off. If you start burning up your U-235 and you have more U-238 that's present in the core, you can get a little bit more fast fission. Small little things change, but these are pretty close to roughly the values, okay? So let's say this is just above 1. Our fast non-leakage here, resonance escape, hold on leakage, thermal utilization, and thermal reproduction. Okay.
Multiply those all together.
So if you multiply those all together, what are you going to get? You what?
I'm not sure.
Not sure. So,
It's the effective one.
okay, exactly. So this is the 6-factor formula, right? So when we started the presentation yesterday, sorry, I wrote those out of order. It doesn't really matter because you're multiplying. If we want K effective, right? But the problem that's posted on Moodle doesn't just ask you for K effective, right? I ask you for what's happening to the neutron population in each step of the life cycle. So if I were to ask, let's add a page here. And let's share this with the people online so you can see. So if I switch for just a second, see if I can go back to the computer for just a second. Put this up. Okay. So if we have 35,000 neutrons exist at the beginning of generation in 1. How many neutrons exist after fast fission?
So in your slides, you have the same spot.
Pardon?
I don't know if they have that.
I couldn't quite hear you.
Yeah, no, it's not a big deal, thank you.
Okay.
I was just wondering about the slides, that's how they saw it.
Fast fission. So if we go back to what we drew up here, you said what percent? 89%. Why 89%? Is what?
Those are the percentages.
Yes. So you're saying after fast fission, you multiply it by fast non-leakage? Because what's the first step?
Okay, you have to do that first.
So the number of neutrons that will exist after fast fission is essentially going to be our number of neutrons times our fast fission factor, right?
What if your K effective is supercritical? Wouldn't it be higher?
So if K effective is supercritical, which is the next question, so some of you guys have jumped ahead, we know that at the end of our whole cycle, we're going to end up with more than 35,000 neutrons, right? So if we don't end up with a final number at the end of each step of more than 35,000, we did something wrong, right? But right here, how many neutrons exist after fast fission?
36,085.
Yes.
You just did that by multiplying.
Right. I took my number of neutrons in the generation times my fast fission factor.
What was the fast fission factor again?
1.081.
Yeah.
This is, fast fission and the leakage happen at the same time.
No, because we first have to have some number that go into fast fission. After those have been taken out, then we're going to have some leak. So it happens so fast, this whole cycle happens almost at the same time. But it does happen in a progression because each factor has to occur in that neutron life cycle for the neutron to go through, right? It can't be absorbed as a thermal neutron until all the fast ones have leaked and fissioned and it's slowed down, right? So we do have to go in order. Even though it's going to happen so fast, it almost basically happens at the same time. Does that make sense?
Yeah.
Okay. All right. If I were you guys, I would take just a minute and make sure you copy down the values for each of those factors. So as we switch back and forth, so I can try to include the folks online, be a little easier. So my next question is, how many neutrons are going to start to slow down?
31,150.
That is not the number I got. How did you get that number, Haley?
I multiplied 35,000 by the
Okay, but we're in a cycle, right? We still fission. Then we leak. So you have to multiply your 35,000 by both to get to this number that starts to slow down.
So we still have to follow that.
Yes, we followed it. So if I,
So 32,150.25.
that is what I got, yes. Right, so number that start to slow down.
So as you move along in the multiplication, you're gonna start with N1 and you're gonna keep multiplying by
Each factor, right? Because the K effective, where we multiply all 6 together, that's what happened to the whole cycle, right? That's what our reactor status is for that generation. So each step along that cycle is another step in K effective. And my plan had been to walk us through the cycle and end up at K effective. You guys just saw K effective in there from the beginning, which is great. Each step along the cycle is what's happening to that neutron population. Yes, Joe.
I thought you said that at every step, the neutrons would be more than 35,000 if we were over 1.
At our end step.
Oh, well,
Once we have our whole 6-factor formula, then we will be. So when Haley gave me this answer, she gave me a decimal. Can we have a partial neutron?
No.
So what would we have to round to? So round the whole numbers on these problems because we have whole neutrons.
Not when you end up with your K effective though, right?
K effective can have decimal points. That is correct. But I'm asking right now, how many neutrons start to slow down? Half a neutron doesn't exist. Okay. Next part. How many neutrons reach thermal energy? No, it's not L sub T.
23,445.
That is what I got, yes. I think that you rounded up and I rounded down though. You said 45, right?
it should be 44.
Not if you use that number in place.
So if I do 35,000 times 1.031 times 0.89 times 0.73, I get 23,000.
That's because after the 0.89, you said you have to round it up, and then you multiply that by 0.73.
Okay, so there might be slight rounding differences because I didn't use this number times that. I put all 4 in.
Well, that's what I was curious about, because I did that originally too, but then you were saying that you should round it up while you're doing the math. If that's, can you just plug in all the numbers all in one and find your K effective?
So you could plug all your numbers in. I'm asking for an answer at each step, right?
Okay.
So this answer is how many neutrons start to slow down. But then I asked how many reach thermal energy. So then I put in each number again, so I have the least amount of rounding error.
Okay, I got you.
Does that make sense?
I'm not
Okay,
for sure getting.
so for part A, the number of neutrons that exist after fast fission. If I multiply 35,000 times 1.031, I get 36,085. Now I'm going to next ask for the number that start to slow down. I'm going to multiply 35,000 times 1.031 times 0.89. Then I get a number that's 32,115.7, We rounded that to 32,116. We don't have partial neutrons, right? When I answer the next question, which is the number that reached thermal energies, I do not multiply 32,116 times 0.73. I multiply 35,000 times 1.031 times 0.89 times 0.73. And then I end up with 23,444.4. I do need another 4, sorry. I got distracted in my writing. Because if I multiply this rounded number by p, I'm propagating a rounding error, right? And I'm going to get further away from the real answer. Whereas if I put each number in here and multiply, I'm going to get closest to the real answer. Does that make sense on rounding? Does that make sense why I have a slightly different answer than you
Yeah,
did?
no, I get it.
If I don't, so not like, not now, but like, so the last calculation didn't round so much at all. Is that gonna be wrong, obviously? Or something like that?
It depends on how much you round, right? So Jack and I were off on this last digit. That's a different number of neutrons. That would have been a wrong answer, right? I probably could have figured out what you did, know you used the right process, and I might like take off half a point for a rounding error. So I'm not as interested in rounding as you guys understanding this theory, right? But every time we round early, we're going to be a little bit off, and we're going to be more off the more we use that rounded number. That's why I'm writing out the factors and remultiplying each time. Okay, so how many neutrons are absorbed by the reactor?
22,507.
Say that one more time.
22,507.
Okay, that's what I got. Oops. How many are absorbed in the fuel? Someone online. How many are absorbed in the fuel? I think my pen just died.
The one that you asked right before that was just with the LSFT.
So,
Or you got the 22 or something.
so when I ask for how many are absorbed in the reactor, yes, we add that L sub T, right? Because we had how many started to slow down? We're right here, right? And we had those that reached thermal energies. We multiply by this. Now we're going to leak out some, and the rest are going to be absorbed into the reactor. So we're going to multiply by our L sub T. Now I'm asking how many end up right here, absorbed by the reactor. Say that a little louder.
18,755.
Yes, that's what I have. You guys online, what'd you get? In this problem, Amber, these will be constant, right? Because this is how our reactor is set up. Until I withdraw control rods and change this number, or refuel and change this number with fresh fuel, or get really, really hot, change this number, these factors will stay constant. But if I ask you a different problem and a different reactor, these factors values could change. So they're not absolute constants, but they are going to stay constant for this problem. Does that answer your question, Amber? Okay, good. Yeah, Joe.
Is that the answer, like before rounding?
Yes,
Would we not round that up?
we would to
Oh.
18,456.
Oh, well,
Is that what you said, Lynette?
Haley answered the question.
Oh,
18,455.
I got 56 when I rounded. Sorry, that's what I got as well. Because it's 5.46, so that 4 rounds up to 5, and then that 5 rounds up to.
I got 18,455.45.
That's 56.
Yeah, so that 5.
45.
So what's going to happen? That 5 will make the 4 round up.
Oh, yeah, okay.
Okay, so sorry, let me try to write this. My pen is suddenly very unhappy. Okay, I'm sorry guys, but my pen died.
Is it possible to share this?
It's not. Zoom won't let me share that over here. Yes, so Amber, and those of you who are online, if you guys want to write this down, eta is 1.031, or sorry, epsilon is 1.031. Eta is 2.102. P 0.73. F is 0.82. Our L sub T is 0.96. And our L sub F is 0.89. So I was asking you guys online, what's the number that you get absorbed in the fuel?
You're gonna be posting this in, or the, American Nuclear Society talk on
Pardon?
Are you showing that here?
Yes, in this classroom. It'll actually be Christy because I'll be with the 153 students.
Okay.
But yes, we'll be playing it in here. Is you have to be an ANS member to participate because it's free for ANS members. So I'll just log in and show it, and that way you guys can watch it without paying. Okay, we'll have more extra credit opportunities. So if you have class and you can't make that one, we'll do more. So for those of you who are online, right here on this cycle, how many neutrons are absorbed in the fuel?
I actually have a question about that.
Okay.
Because I got a higher number than what we came out with. So let's see. I ended up with 38,793. But we started with 35,000. So I thought
Because our K effective is greater than 1. We're increasing neutron population, which means we're increasing reactivity, which means we're increasing power.
oh, it just kind of goes up. It like builds onto itself. So we get higher and higher, like the more.
Yes, so
each
now,
generation.
if we change nothing else, and we still have our K of 1 point whatever it is, now we're gonna start here with 38,000 neutrons, and do this again, and we'll end up with something like 40,000. This is an increasing power. We're increasing power, which is increasing neutrons and increasing reactivity. All of those three are synonymous. Let me answer Marcus's, then I'll get Haley. So Marcus, I think that you rounded your last digit wrong because this is what I got. But you probably did the math right. Probably just around here. Haley and Jeffrey.
So is the end number going to be N2, and then you start the cycle over again, like the same way, except for you use N2?
Yes, and then we're calculating in 3, right? So once we've gotten into, now in 2, we were just born, we're gonna start a new cycle. And we're gonna end up producing in 3.
Is that what you're asking in problem 3, to do all those steps again? A through F, or whatever, just with the second generation?
No, with the generation and the factors that are in that problem. Because you have a different number of neutrons and you have different values for your factors. You have a different reactor.
If you just multiply them all together, you just keep your K effective, and you could just keep multiplying each generation by your K effective.
Yes. So, but you wouldn't round down, Marcus, right? Your first rounding step would be 18,455.5, right? Because you have to round that. Then your next round of rounding would be that. Because that 5 means the 4 has to round up. And then that 5 means the 5 has to round up. Does that make sense?
So how did you answer Matt's question?
So if the first thing I did was take in1 times my K effective, right? I would end up getting this in2,
And just round it, and that would be the end answer?
the end answer. But that doesn't tell me
What
each
step?
step, right? Because I'm asking, so a good way to check yourself is if you calculate K effective and multiply this, and you get that answer, you should get the same answer going through each step here at the end, right? So, how many neutrons are produced from thermal fission?
$38,793.
Yes. Are these neutrons that are produced from thermal fission fast?
Say so?
Yes. They're always born fast. So this is why N2 would now start going through this cycle to leak and slow down and create fission, and then create N3, which starts fast again. Then we would do it again and again, and that's how the nuclear chain reaction lives in our reactor. I don't have any paper towels.
I'm gonna grab some.
So that's the order that you would do it in, E, and then LS, and PLCS.
Yes. If I ask you to go in order, right, it's possible that I might ask these questions out of order, right? If I ask you, just off the bat, you got 20,000 neutrons, here's your terms, tell me how many start to slow down. I'm asking you to jump to here, right?
But you still have to go through E to get to alpha then.
Yes, you would have to multiply by both, but I'm asking for this value instead of this first one, right? I went in order at each step in this example. It is possible on a test question, I might skip parts A, B, and C and ask you D and F. Because I want you to know what I'm asking about the cycle, what happens in each step.
You basically just subtract the ones that don't slow down. So you would have to, so if you come up with a total number, you would subtract that by how many you started with.
We don't subtract when I'm staying on the cycle. If I asked you how many leaked,
Yeah.
you would have to multiply by this and 1 minus this. But if I ask you how many start to slow down, I'm asking you how many get right here, which is multiplying this by this.
Oh, so you're still gonna go in order. Okay.
I might just not ask you to tell me the number here and the number here, but I might just ask for the number here.
I got you.
You still have to do each step,
Yeah.
but I'm just asking for this
Okay.
number. Does that make sense?
Yeah, I was confused.
And then Jennifer.
So are we gonna be able to have a great sheet on these?
Yes. You will have an equation sheet for these tests.
An equation sheet or self-generated?
Self-generated cheat sheet, 1 page, whatever you want. Yeah, Joe.
Say again, how many neutrons leak? It's 1 minus the second number that we received?
So how many leak fast
All right.
and how many leak slow is 1 minus that number.
Okay.
Because we're interested in the ones that don't leak, right? If they leak out of our reactor, we're no longer controlling them or making fission. We no longer care. Your reactor engineers are going to design reflectors to make this number as close to 1 as possible, right? So there's no leakage. But you're always going to have some. Okay. What is the K effective for this cycle of this reactor?
1.108.
That's what I got, 1.108. Everybody online? Do you see how we got K?
Yeah, you just times them all together. Yeah, there you go.
All of the factors together?
All of the factors. This is the 6-factor formula for K effective. Physically, it describes the life of a neutron generation in our reactor. Mathematically, it's the factors that give us K effective. So when we say we have a K of 1 or a K of 1.1, and we know that we're increasing or remaining steady, or if we're subcritical, we're decreasing, we know that the neutrons are doing more of this, less of this, or the same of this, right? So it's mathematical and also physical. Do you have a question, Kyle?
What did you say it was?
1.108. Amber and Porter, did you guys follow that? Did you see what we did? I know you can't see the screen very well.
The end number.
Okay.
So on the, so you not round on the one, on the K effective, you just do 1.08, not round 1.11.
So on K effective, I would usually keep 3 or 4 digits, probably to make it easy. Since I said 4 on the atomic binding energy calculations, we should probably keep 4 on this one just to be consistent. I wrote 1.1084.
Okay.
Because again, if you're just a little bit above 1, if you're 1.0001, you're still increasing in power. And if you've been asked to keep the reactor at steady state and you're not exactly at 1.0000, you are going up in power. And even though those are small numbers, they do matter when you're operating.
Isn't 1.108, wouldn't that be like a rapid increase in power?
Yeah, this is a pretty high K. We jumped from 35 to 38,000, right? That's a fairly good K. And what we're going to calculate for the last part is reactivity. I'm going to write this equation down and we'll pick up there on Thursday with what this is. But reactivity, which is represented by rho, which is a little italicized looking P, is K minus 1 over K. This is the easiest unit for us to determine how fast our reactor power is changing. And this is fun. We have a whole lesson planned a little bit later this semester, just in all the myriad units you can have of this. Because you can have dollars and cents, you can have delta K over K, you can have percent milli. You can express this in almost infinite ways because it's such a versatile and useful piece of information about your reactor. So we're going to start on tomorrow explaining this a little more. Then we're going to step away from it for a minute and we'll come back to it in a few weeks and throughout the semester. Yeah.
What is K? What is K again?
K is our multiplication
Oh, that's your
factor.
K effective?
Yes.
So K is the multiplication factor and the infinite multiplication factor is the rho.
No, this is reactivity. Our infinite multiplication factor is K infinity. And it assumes you have a perfect core without leakage. So it's just the 4 factors that are not leakage. Because if you have an infinitely large reactor, you literally can't lose any neutrons, right? Do you have a question, Kyle?
Yeah, I thought my second generation neutrons at the end of it was 47,309. Where did we get that number?
The number of neutrons at the end should be 38,000. What was it?
793.
793.
So where did I get that?
That should be multiplying all of these factors times in 1.
Is that just an N or is that Ada?
That's Ada. I'll make it a little more tail. Sorry, it's really hard to match up with this pen.
I think when Mike taught us, he actually taught us with the LGH too.
Did he?
When we were looking at like mermaids and stuff like
That's
that.
what your book says.
Yeah. Because my book is
That's what I'm saying, where did I get
from the late 80s. It was published. And that LTH was the standard. This is how they put it in the newer books. So I've tried to adapt. But I'm sure Mike, when he learned
Old
it,
school.
learned the LTH. So as long as it doesn't confuse you when you guys
No.
know it's supposed to be the same thing. Okay, we're just a couple minutes over time. Any other questions before we end class? I'm fine with staying here and answering some until Tom gets here.
So I just wanna, like, make sure I understand this. To get the KF, you take the number that you get at the end and divide it by the number you started with. So like, I did the 38, whatever, divided by 35,000, get the 1.1.
Yes, and so we're gonna talk about this Thursday too. But another way to get K is to compare the number of neutrons in your generation. Because K effective is comparing what's happening in one generation to the next, right? Are we going up in neutrons? Are we going up in power? Are we staying steady? If N1 equaled N2, K would equal 1. So we have a critical reaction, right?
So then I'm supposed to take N1 and divide by N2?
Sorry. It's 2 over 1.
Okay. That's what
I just,
saying you can't, you still can multiply all these terms.
you have to do. You have to do that.
No,
2.
not for the ones up there, you just multiply all the terms, you don't put that in.
And so this equation will give you the same answer,
Just without the neutral.
just just another way to express K.
Just multiplying epsilon all the way through. And
Because
then-
K is telling us something physical about the reactor, so we can get to it mathematically a bunch of different ways, depending on what we know about a reactor.
You should end up with the same thing as your second generation. That's why when you got yours, I didn't do it.
We're gonna pick up here on Thursday, so if you're a little confused, we're gonna do more of this same concept Thursday.
And we're gonna find the reaction B.
Yes.
Yeah, I don't know what happened, but somewhere along the lines, I went to, from the, thermal utilization, from there was 18,456. I went to like 48,709. And we were talking about it, so I thought I got the right answer. I don't know where I got that answer though.
If you wanna come by office hours,
I got it.
You have to,
it's
okay.
fine.
before I end the Zoom, any questions online? Okay, we're gonna do more of this on Thursday. It will definitely be easier if you guys are in person and can see the board. But I will still try to have it on Zoom where you guys can follow.
Is it effective
See you later.